and the application software is SPSS. So first I request you that don't concentrate it on the software part. Every software, SPSS, SAS, R, Stata, EViews, even the Jamovi, everyone express the results in a form. And what is our main purpose is to that is explanation, given the proper explanation of the results. That means understanding of the result sheet, how you understand the result sheet. That is the important thing. So I don't know that this multivariate analysis and underneath the principal component analysis, uh, whether it is possible for me to cover the whole issue, but I will try. And some applications of this PCA through spaces I will try, but for the understanding of that is expressing the result in uh, respect of their significance, that is the knowledge regarding the behavior of the data is very important to us. So uh, that is the most important thing. And another request to all, that if there is any type of query or questions, anything uh, unclear understanding, you directly interrupt me and then raise your questions. So I'll
স্যার মোবাইল রাখবেন প্লিজ।
হ্যাঁ হ্যাঁ ঠিক আছে। Is it visible?
Yes, sir.
Yes. Okay, just wait 1 minute. The screen is visible to all, no?
Yes, sir.
Okay.
Yes, sir.
So what is PCA? PCA is a data reduction technique, and it is developed by Harold Hotlings in 1933. So before entering into the hardcore prime principal component analysis, let us try to understand the variables in terms of sensibility. That is, which variable is more sensible, which one is less in that. That means among a set of large variable, which variables are more significant to explain some, for example, social or economic or political or geographical and even environmental facts. So here we assume a number of variables. The variable number is identified as a p, and on each variables we take the data, and the data set consists of n observations, n number of observations. So you find the data matrix. It is visible on the screen. That is X, capital X is the data matrix. That is the values are x1 1, x2 1, and dot x1. This is the first column of the matrix, which shows the data set of the first variable. Similarly, second column is the data set of the second variable, and similarly, last column is showing the values of the pth variable. So don't make it complex in terms of I am using the notations like n or p. These guys, these are actually the real numbers. So depending on the value
Cross-section data.
yes,
It's a cross-section data.
It is a cross-section data. Yes, yes, it is a cross. You can consider this is a cross-section data. So considering the values of such P and N, this is a big data set. I'm not mentioning which one is dependent, independent, this kind of thing. Suppose these are the informations regarding the different variables. So I arrange them in a data matrix. So here we are not mentioning which are under the category of dependent and which is under the category of independent variables. I'm not mentioning. Rather, we treat each as a separate variables. These are the separate variables. Actually, what is happening, dependence and independence variable creation is possible only when we deal with some specific area of research of interest. That is what we are trying to do. I'm not fixing any that kind of things, that is any research idea. So now suppose for example, I'm not fixing the dependent variable, but suppose we are interested regarding the mobile data recharge behavior of the college going or university students. This is our field of interest, that is what is the mobile data recharge behavior. So several variables can be clouded over such facts, and I identify some of the variables as like this. These are the 10 sets of variables. First one is income class of the family of the students. That means whether the students are belongs to rich or middle income group or poor families, like this. Second factor is family size. This is the important factor which influences the data recharge behavior. Third important factor is considered as a residence. That means whether they are living in rural or urban or peri-urban areas. And fourth factor is subject of the students. Subject of the students means, for example, a students is under Sanskrit and a students under the course journalism. The students in journalism is bound to use more data because a lot of information. I am not saying that the Sanskrit has not more information, but rather in compared to the Sanskrit, journalism has to have some lot of information in the web. So number 5 is like this, that is social relationship. For example, today we are maintaining the WhatsApp, that is relationship between the friends or any circle. Sixth one is stipend received by the students, that is a scholarship, which is also influencing the data recharge behavior. And the other is pocket money received from the family. Surely it is an important factor. And the involvement of the students in doing private tuitions, because some PG students or some college students are doing private tuitions, and that is the involvement of the students in private tuition is an important factor. And there may be some options like part-time job involvement, and the last one is considered as interest in doing online courses. For example, the courses of Swayam or MOOCs. This. So these are the 10 variables identified considering the data recharge behavior. Now we collect the information. Suppose we collect the information about such 10 variables from 1,000 students. So it will be a size of 10 cross 1,000 data matrix, because 10 variables and each variables have 1,000 values, and that create the data matrix. Otherwise, you have to deal with 10,000 data points. So it is a tremendous task to consider anything, to derive anything from this data. It is a tremendous task. So then one question comes in our mind, that whether all such 10 variables are equally significant to explain the mobile data recharge behavior of the college or university student. Surely not. That is the expected answer. Not all are equally significant. Actually, some are explains a lot, some are moderately explained, and some are with low explanation over the mobile data recharge behavior of the college student or university students. So thus, it is a significant task for us to identify the variables as per their explanation power, and also identify the level of such explanation power for the specific variable. So in the above mentioned example, that is I'm considering the data recharge behavior. identify all the 10 variables. Suppose we identify the 10, I'm not mentioning the which process or what process. Suppose we identify the 10 variables in terms of their explanation power over such mobile data recharge behavior. And I found this is the result. So just look the results. So among the 10 listed variables, we found that only the first 3 variables, that is income class of the family of the students, and that is rich, middle, or this family size, and the residence, explains 94.01% of the sample data recharge behavior. Here you find that the income class explains 54.12%, family size explains 23.24%, residence 16.65%. So that means these 3 are the major variables, that is, which explain the mobile data recharge behavior of college students or university students. So these 3 in a sum, they are explaining 94.01% of the total behavior. And the remaining 7 variables explains only 5.99% of the sampled mobile data recharge behavior of the college students. So from this example, it is clear to us that income class of the family of the student, family size, and the residence are the 3 main variables to explain the sampled mobile data recharge behavior of the college or university student. So if suppose after knowing this, suppose without knowing this, suppose if any researcher considered only these 3 variables without considering all other 7 variables to deal with the issue like mobile data recharge behavior of the college or university student, he is very much correct. And also time and cost saver also he is. And his research forecasting gives us a prominent result. So we say that the result is wonderful. That means the students, if he catches only the first 3 variables without considering the remaining variables, then his result is wonderful because he is a time saver, cost saver, because he doesn't collect the other informations. But his result is, if anyone collect the whole informations of the other 10 variables, total 10 variables, then in compared to that, the first students who collects only the 3 variables informations, we say it wonderful. It is a beautiful process. So the identification of the variables over some research objectives, because there is always a research objective behind anything, in terms of their contribution among several variables, this problem is known as data reduction. So we have to reduce the data. So such data reduction can be done by several ways. So such data reduction can be done by several ways. One of them is indexing. And you may have heard about the entropy methods or that formula in people of geography, people of economics are used, that is actual value minus minimum value divided by maximum value minus minimum value. That kind of normalization technique. We generalize in case of entropy method, for example, we generalize the impact of several variables into a single entropy. That means combined all the variables into a single entropy. And this is the one way. This is one way of data reduction. That means combining all the variables into a single index. And PCA is doing that process what I'm describing. That is identifying the variables in terms of their relative explanation power. So rather suppose in this case, in this example, you find that it is a 10 by 1000 matrix. This case, we may transform the matrix into 3 by 1000, because 3 are the important variables, not the others. Others are important but very insignificantly. So we can remove them. So PCA is doing this process. These actually gives us the information that which one are the important. So it is also termed as a dimension reduction method. that is how to reduce the dimensions of the matrix. So before entering into the PCA, we have to make some senses regarding the variance covariance matrix. Up to this, if anyone have some unclear understanding of this, you may ask the questions up to this without going to the variance covariance part. If you have any queries or questions, you may ask. Okay, I think it is okay. So we are considering that is a data matrix. Suppose we are considering a data matrix. So size is n cross p. That means number of rows is n and number of columns are p. So number of columns are like before what I am writing, that is x, which is in the form of p number of variables and n number of data points. So if I consider this is a data matrix, and you know the formula of variance and covariance. So if there are suppose three variables, if there are three variables, that means since the p number of variables, so we can, how many covariances will be created, that is given by the combination formula, that is PC2, and it is derived by factorial p by factorial 2 and p minus 2. For example, number of, suppose three variables are there like x, y, z. So how many covariances are there? That is 3C2. That means factorial 3, factorial 2 divided by factorial 3 minus 2. That is 3 covariances are there. And the covariances are what are the covariances? The covariances are covariance between x and y, covariance between x and z, and covariance between y and z. And also there are the variances, the variance of x, because three variables, if there is three variables, the variances are variance of x, variance of y, and variance of z. Now look, variance of x, that means you know the variance formula of variance of x, that is 1 by n summation of xi minus x bar whole square. And that xi minus x bar whole square can be written as xi minus x bar multiplied by xi minus x bar. So the variance can also be expressed in the form of covariance. So we write the variance of x as a covariance between x and x. Similarly, variance of y can be expressed in the form of covariance of y, and variance of z is covariance between variance of z. So when there are three variables, we can form the variance covariance matrix as follows, that is sigma square, and you find this, that is covariance of x's, and the diagonal elements are covariance of y and covariance of zz, and the off diagonal elements are covariance of xy, covariance of xz, and covariance of yz. That off diagonal elements also represented into the lower off diagonal triangle, that is covariance of yx, covariance of zx, and covariance of zy. And here actually what is happened, if we look at the covariance formula, what is the covariance of xy? That is the covariance of yx. These values are similar. So in suppose we write the matrix in this form, in the numerical figure, that is 12, 15, and 22 are the variance of x, y, z, and the variance covariance between x and y is 21, covariance between x and z is 20, and covariance between z and y is 18. And the upper, it is not required to write the full matrix because the same reflections will be happening. So in case of the diagonal values of the variances, one thing is important you have to remind when you consider the variance covariance. Why I am dealing with the variance covariance, that I will come because it is very important role in case of understanding principal component. Diagonal values are the variances, and the off diagonal values are the covariances. So variance covariance matrix is such thing that the diagonal values of the variances and off diagonals are showing the covariances. But it is noted that always it will be a square matrix. That means the number of rows and number of columns will be equal. So since there are three variables x, y, z, the matrix size is 3 cross 3 and or 3 by 3. Similarly, if the matrix is order n cross p, that is the previous x matrix, there are the n number of observations and p number of variables like the x matrix. So if I construct the variance covariance matrix, That is this sigma square, that is between the covariance diagonal elements are covariance of x1 and covariance of x2 and so on. By this way it is running, and the off diagonals are the actual the covariances. So off diagonal, if these off diagonal elements, in case of 3 variables or in case of many variables, if the off diagonal covariances are non-zero, that means they are existing. Suppose covariance between x1 x2 is in the 3 cross 3 covariance matrix, we found the covariance between x and y is 21. That means it is not zero. That means it is something. So if the off diagonal covariance are non-zero, that means their covariance means what? That means if it is covariance is something positive or something negative, anything, it will generate a value for the correlation coefficient, because you know the correlation is the ratio between the covariance and the variances of the two variables, standard deviations actually. So then when the covariances are non-zero, then there will be possibility of interdependence between the variables will appear. So we cannot say such interdependence as a relationship between dependent and independent variables, because I'm not asking that y is the dependent, x is the independent, z is the independent, y x is the dependent. I'm not mentioning by that way. There is some relationship. I collect the informations regarding x, y, z, 3 variables, and I found that their covariances are non-zero. That means some kind of interdependencies are there between the x and y, between the x and z, and between the y and z. But such interdependence is not in the form of any relationship like dependent independent variables. Rather, it is a kind of, you may call it as interdependence. For example, if you have some knowledge in regarding the multiple regression, I write one multiple regression equations, that is y is equal to beta 1 x1 plus beta 2 x2 plus beta 3 xt and so on, beta p xt. So here y is the dependent variable. Say it is the amount of money spent for mobile data recharge behavior by the students. It is another information. Suppose in our previous example we consider the 10 variables, and without this 10 I am considering a new variable, that is suppose the amount of money I spend for the mobile data recharge per month. And x1, x2, x10 are there. That is a set of 10 variables which are discussed earlier. And this is done specifically under the multiple regression technique. But one restrictions under this multiple regression technique is that the absence of multicollinearity. That means what? That means the covariances between x1, x2, between x1, x3, and so on between x1, xp, or here if we consider the 10 variables x1, x10 is 0. There is no relationship between, because if there is multicollinearity, you know what kind of problem, R square will be high, regression results is not establishing the true relationship. There is several kinds of problems due to the multicollinearity, and multicollinearity comes from where? That is if the independent variables are becomes related to each other. So the covariance between the independent variable like x1, x2, x1, x3, x1, x10, this equals to 0. Similarly, x2, x1, x2, x3, x2, x10 or xp, these are all are equals to 0. And similarly follows for all variables xp, x1, xp, x3, and xp, xp minus 1. That means really every combinations between the variables are all 0 except their own combinations. That means if there is no multicollinearity, then the situation looks like the variance covariance matrix sec becomes this, that is the diagonal elements, that is in case of multiple regression technique actually, if we look, the off diagonal elements of the matrix become 0 and only the diagonal elements are exist. So so why I am not telling first that we are not discussing dependent independent kind of relation. First consider this. But suppose we have such data points with p variate, for example 10 variate, which are not separated as independent dependent variables, we can split or distinguish or separate these variates in terms of which one is dependent and which one is independent. Then we go to multivariate analysis. That means if there is no such rule, that there is no such way, we do not know which one is dependent, which one is independent, then what we do? We can do for multivariate analysis. In multiple regression, there is one dependent variable and separate independent variable exist, and we do the regression. And there you must be careful about the situations like multicollinearity, these kind of things. But in multivariate analysis, all the sets of the variables are not related in terms of dependence in the independence sense. They are related in terms of interdependence. That means the covariances are exist in case of multivariate analysis. So multivariate analysis is interdependence method, but the chances of multicollinearity still persist. Still there is a chance of multicollinearity, and to avoid the issues of multicollinearity, what we are doing, we considering the factor analysis as the way out. That is the PCA. So in PCA, what is done is basically combine some multiple correlated variable in some single indexes, and then we go for multiple regression. If we are interested, then you go for multiple regression. That means we are extracted the variables which are significantly influences our objective, our dependent variable, and then after extraction, that means we are reducing the dimension of the existing matrix. If the matrix have some particular number of row and particular number of columns, in terms of the number of the variables and their enlisted number of observations, we will try to reduce, that is, we will try to lowering the dimensions. First, what we do, we lowering the dimensions, and we are doing orthogonal transformations, or it is identified as orthogonality of the transform dimensions, which is known as principal component. So we consider that means what is the basic objective of PCA is that it is possible that the variables are multiple correlated. That is, they are correlated each other, and without caring this, without considering the problems of multicollinearity, what we are doing, we are doing some single indexes, because multicollinearity is not an issue there. Because why? Because we are not considering any dependence independence type of behavior. We are issues, or that is we are just.
Could you explain by some example?
Yes, I'll come to that. I'm giving example. That means in that example, that is what I'm giving you earlier. That is 10 variables are there, and now there is a separate dependent variable. Suppose there is a separate dependent variable. Now in your mind, and you find that in reality, you find that you check the multicollinearity and find that these variables are heavily multiple, heavily multicollinearities exist between the variables. Then what you will do? It is not possible for you to run the multiple regression. Okay, then what you will do? You will try to remove those variables which are actually created the multicollinearity problems. This is the general process what we follow in case of multiple regression to remove. There are the several processes for the removal of multicollinearity, but this is not discussing here. I am discussing what? There are the 10 variables. I'm looking the problem in separate angle. That is there are 10 variables. There are these 10 variables I have to identify in terms of their variability. That means variability in what sense? That means in terms of their influence over the specific areas among the 10 variables. So that means what? That means there is something. How it is done, how it is working, I will come to that. But what is happening? That means I will lowering the dimensions, I'll reducing the dimensions, and orthogonal transformation is the most suitable way for such lowering of dimensions. And these transform dimensions, when I get the new dimensions, then each and every element, each and every dimensions of that new matrix are known as principal component. This is the basic idea. That means there are the 10 things, 10 variables. Now, suppose these 10 variables are identified, you identified them as x1, x2, x3, x4, x5, x6, x7, x8, x9, x10. Now you run the PCA. Then you get the x1, x2, x3 are the important. You do not get x1, x2, x3 the important. They are appeared as a separate variable in the form of z1, z2, z3. That is, these three components are important. They are not appeared as the same variable. They are appeared as a different component. I'll come to that story. So what is your easiness here? That means it is now easy for you to handle the problem. That means you are reducing the dimensions. This is the basic thing of PCA, basic story of PCA. So here we start the problem of discussions, that is considering two variables x1 and x2, and the data matrix is like this. Suppose the data matrix and the data set for the x1 is identified as x11, x21, and xn1, and x2 is identified as x12, x22, and xn2. This is the data set for the second variable. And what we are doing, we plot this data set over the axis. Just look at the figure without considering the dashed blue or dashed red line. Do not consider this. I just plot the data set, and the data sets are, you find the black dots at the data set. Now, suppose we are interested in the spreadness of the two variables. That is how the two variables are what? That variables are x1 and x2. Now we are interested regarding the spreadness of the two variables x1 and x2. So spreadness is measured by, without any statistical or mathematical knowledge, what is the spreadness? That means where in the right hand side, how much the maximum data of a maximum value of x1 is we get, and the left hand side we get, and we draw the two blue dashed lines considering the maximum spreading of the data set for x1. Look at the two blue dashed lines, that is considering, that is and between the gap between the two blue dashed line is identified here by a second bracket, and that is what shows the spreadness of x1, and it is measured by the blue lines, that is thick blue lines between the two terminal values of x1. And similarly for x2, the vertical red dashed line measures the spreadness of x2, and that is by the thick red line showing that spreading. So the spreading of the variables are measured by the distance between two such red and blue lines. The spreading of such variables you may call these are as variability. Is how the values, because if you think about the formula of variance, what is the formula? That is 1 by n minus 1 summation xi minus x bar whole square. That means what? How the values of x is spreaded from their central value, that is the mean. So here the measurement is like this, that in rigorous term it is used here, that is, it is the gap between the two terminal values, highest two terminal values of x1, and similarly for x2. So we can call the spreading of such variables as the variability of the individual variables. And the such spreading or the variability, when you expressed it in terms of the statistical theory, it is called the variance. And we know the formula of variance for the x1, it is identified as S11, that is 1 by n, or some books it may be considered as 1 by n minus 1, both are true, and summation x1i minus x1 bar whole square. And similarly for x2, it is identified as S22, that is 1 by n x2i minus x2 bar whole square. So in this case, for the data set, same data set, if we consider the variance covariance matrix, look at the covariance of x, that because x is the main matrix, data matrix. So if we find out the covariance of x, That means what? The diagonal elements, that is S11 and S22, are shows the variance, and S12 or S21 will show the covariance between x1 and x2, and that covariance will be stated as this formula, that is 1 by n minus 1 summation x1i minus x1 bar and x2i minus x2 bar. So here note that the data matrix of the two variables x1 and x2 are represented in some sample data, because we are considered this data as the X data matrix. This data matrix is chosen from a particular population. That means it is a sample data. If it is not, if it is a population, then you may call it that the variance covariance matrix for the population. This X is this covariance of X is the variance covariance matrix for the population, and we can say this population variance covariance matrix in this form, that is sigma 1 sigma 1 2 sigma 2 1 sigma 2 2, where the diagonal elements are the variances and the off diagonals are the covariances. Now, whatever that means, it is possible. You cannot think about the population or the sample. Anything, it will be happen. Now you can extend this. You can extend such constructions. That is you can construct the correlation matrix also between the x1 and x2. And how it will be? The correlation matrix looks like this. That is 1 at the diagonal elements, because 1 representing what? That means the correlations of x1 with x1, that is always 1, and similarly the correlation matrix of x2 with x2, that is identified as 1. So the diagonal elements are 1, and the off diagonals are 1 2 and are 2 1. So the diagonal elements of the correlation matrix is unity, because it interprets the self-dependence, but the off diagonal elements are expressing the correlation between x1 and x2. So that is given by the R12 or RT1. That is a simple correlation formula, that is S12 divided by root over S11 and S22, and this S11, look, this S11 which is derived earlier, this S11 or this S11 or this S22, these are expressing what? These are expressing the variability. S11 expressing the variability of the data set x1, and S22 is expressing the variability of the data set in x2. In figure, that is expressed by the gap between the two blue lines for x1 and two red lines, that is the vertical distance, gives us the variability for x2. So now I am doing one thing. What I am doing, just one. Suppose we rotate the x1 and x2. Suppose we rotate the x1 and simultaneously x2 will rotate. So I rotate the x1 and x2 axis anti-clockwise. I rotate the x1 and x2 axis anti-clockwise by angle theta. And the rotated figure looks like this. The x1 axis now placed to z1 and x2 axis now placed to z2. So is it clear how the rotation made? Okay, it is. Then simple anti-clockwise rotation. Okay, it is. I just change that this x1 axis rotated towards this, and automatically if this is the angle is theta, then automatically this axis also moved by the theta angle, and the new x2 axis is this. This is the z1 and z2. Okay. Okay, it is. Everyone, is it clear? Am I audible?
Can you explain again?
Pardon?
Hello, sir.
Yes. Yes. I think your network. Am I audible to all?
Yes, sir. Yes, sir.
Yes, sir, audible.
Yes,
Okay,
sir.
okay. The rotation kind of thing is understand. It is clearly okay to all. It is just a simple rotation of the axis. Nothing is there. So if I rotate the axis and again I place the Z1, Z2 similar as just the before figure, the figure looks like this. Just look at this figure. If I put the Z1, that means what? That means just I rotate the page. Suppose I rotate the page by this theta angle, the x1 axis moving, x1 axis moving to Z1 and x2 axis moving to Z2. Then again, after drawing the Z1, Z2, I make the page by such a way that the Z1 and Z2 place to this. So look at the position of the points in terms of Z1 and Z2. Look at the position of the points in comparing these two figure, that is figure 2 and figure 3. If when I rotate the axis in terms of the theta, look, the position of the points is here in terms of the Z1 and Z2. Now it is changes by this way. Okay, is it clear? Just observe. No mathematics, no calculation is there. Just observe it. Okay. If you do not respond, then it is quite a tough job for me. If there is any problem, because
Yes, sir.
okay. So now measure again the variability. Now look again the variability of the variables measuring by the dashed line. What you found? The variability of Z2 becomes quite low. That is, the variability of Z2, that is the thick red line, becomes smaller and the blue line becomes quite substantial. So the variability of Z2 is now negligible and the variability of Z1 is quite substantial. This kind of transformation, what we done this before, that is by rotation of the axis, such transformation is known as orthogonal transformations. And we can say that by such transformation, what we between the two variables Z1 and Z2, only variable Z1 has a significant one in terms of variability. The variability of Z2 is not very significant. So we can concentrate on only Z1. Thus, originally our data matrix X, which is two-dimensional, but in terms of variability, we found that it becomes one-dimensional because Z1 is important, not Z2. Is it clear? In terms of variability. Okay, I just give an example.
Can you repeat this question?
Pardon?
Can you repeat this portion?
Yes. Just look at the figure. Look the first figure, that these data are placed by this way. Now I rotate the Yes. Now I rotate the axis by this way, that is anti-clockwise by angle theta. So look, don't look here the x1 and x2 axis. Look the z1 and z2 axis, and consider the position locations of the points. These points are distributed over this z1 and z2 axis by this way. Now place the z1 and z2 axis in terms for your greater visibility by 90 degree, and the position of the points looks like this. Is it okay?
Yes, sir.
Now measure the variability in terms of the principle which we applied earlier, that is making the maximum distances between the x1 in terms of z1 and in terms of z2. So what we found? The gap for z2 is now minimum, negligible, but the gap for the z1 is maximum. That means what? That means the variability, because it's explained the variability. So if we transfer, that is it is a geometric explanation. That is, if we rotate or transform the variables in terms of orthogonality, we found that the variability, in terms of the variability, now the variables can be separated. Now the variables can be identified, which one is more variable, which one varied substantially, which one is varied by low. So if we extend these cases for many variables and many dimensions, which is not possible to give here. That is, if we extend the cases for many variables we can reduce the number of dimensions and in terms of the effective variability. And principal component is serve such purpose of reduction of dimensions. This is the first thing we have to understand, that this is the basic working of the principal component is starting from here. For example, earlier we have considered p number of variables and n observations, and n observations of vector x, and the orthogonality original dimension vector is written by this way, that is x11, x12, x1p, and so on. So it is n cross p vector. And what are the variable vector? This is the data matrix. This x is representing the data matrix, and this x is representing the variable vector. That means if we consider how many variables are there, the variable vector can be written by this way, that is x1, xp, xp. So how PCA analytically serve the purpose of reduction of dimension? That is important. How PCA is serving the purpose of reduction of dimension is the most important, because why? It will help us when we get the output of PCA derived by any statistical software. That is, when you get the output of SPSS after running some PCA, you have some results. But how you explain the results? That means how you explain that the dimension is reduced and what are the now significance. Not necessarily you have to read the other research paper of this, but if you have some clear idea regarding the behind calculations, how in behind the software calculates the thing, then it is easy for you to understand. So now again we consider the figure number 2, that means this figure, this rotation figure. This figure again I consider. So I consider this figure here again. So consider the case of the two variables earlier, that is x1 and x2, and they are now converted by the theta angle, and you move to get z1 and z2. So look at the point M. Consider the point M, which is given by this black point, black dot, and what is the ordinate of the point M? That is on x1 axis. It will on x1 axis its ordinate is m1, because this distance is m1, this horizontal distance is m1, and this distance is m2. So the ordinate of m is m1, m2 as per the x1 and x2. Now when I shift this axis to z1 and z2, so what we will do? There is some mathematical calculation, and those who are not from mathematical backgrounds, I just suggest them, just listen. Do not. It is not a very important one. That means what I am doing, that means from here, that is from M2 point, I draw two perpendicular. One is over Z2 and one is over Z1. And from here, similarly, I draw two perpendiculars. One is on Z1 and another is Z2. And I get the point like M4 and M3. And here you get the point like M5 and M6. So considering these points, what we get, we have to express M, which is earlier expressed in terms of x1, x2. Now when I transform it in terms of the z1, z2, they are expressed by this way. That is, z1 is expressed as x1 cos theta, x2 sin theta, and z2 is expressed as minus x1 sin theta, x2 cos theta. If I transform the angle, that is z1 by theta amount with respect to x1 axis and with respect to simultaneously x2 axis. So if any point whose ordinate is x1, x2, suppose the ordinate of the x1 is ordinate of the point M is x1, x2, and that can be transformed in terms of z, that can be expressed in terms of z. That is, when that means understanding is what the point, any point, any point in the graph have some amount of x and some amount of y. So here the origin, here the x and y are not there. The variables are x1 and x2. So M point have some x1 and have some x2. Now I am changing the axis. What way? That is by rotating it some by angle theta. And what is the ordinate of point M becomes? That is by this way. That is orthogonal transformation. I am not going to that mathematics. The values of Z1, that is, it has some Z1 and it has some Z2, because M is not a point on x1, x2 now. It is a point over the Z1, Z2 axis. So it has some Z1, and Z1 is what? How x and z are related. That is, Z1 is x1 cos theta plus x2 sin theta, and Z2 is minus x1 sin theta and x2 cos theta. And we can write them in terms of the vector matrix notation. That is, we actually which is actually derived from the these things. These equations Z1 and Z2 are actually derived from the properties of similarity of triangles, which is the mathematics of class 11. So those who are without mathematical background, I request them just consider the interpretation as given. Just consider this as given. There is no such heavy mathematics or this kind of things. So such transformation of point M from x1 and x2 to z1, z2 space can be written in terms of the vector matrix notation as, look here, that is z1, z2 is equal to cos theta sin theta minus sin theta cos theta x1, x2. That means there is z1, z2 is consists of one matrix, and cos theta sin theta minus sin theta cos theta is another matrix, and x1, x2 is the variable, original variable, and it is transmitted to a new variable z1, z2. So we can write this if there are many variables like x1, x2, and so on. If there are many variables, we can write this in the form of, that is, z is equal to a transpose x. This is the transpose. This is considered as transpose matrix, cos theta sin theta minus sin theta cos theta, where the original matrix is what? Original matrix A is considered as in this form, that is cos theta minus sin theta and sin theta cos theta. Because if this is the original matrix, everyone knows that when I make the transpose, the rows are comes to the columns are comes into the rows. So if it is the original matrix, if A is the original matrix, you look the row, that is the cos theta and minus sin theta, it comes into the columns here, that is cos theta, and this is minus sin theta, and again this row is come into this column. So each of the row have some values of cos theta and sin theta, and we call the matrix, the first column, that is cos theta sin theta, is identified as A1, and the second column, it is identified as A2. So the that is make puzzle in terms of cos theta sin theta. This is difficult. This is a huge mathematics. Don't ignore this. So just this cos theta as A11, and this is A21, and this is A12 and A2. And or you may simply write it as A1, A2. That is, this A matrix can be written in this way. Actually, what is happening? That is, A11 is the cos theta, A12 is the sin theta, A21 is the minus sin theta, and A22 is the cos theta. And what is A1? If I write in this way, what is A1? A1 is the cos theta sin theta, and A2 is the minus sin theta cos theta. So whatever may be, look at the thing. But originally, the things is that the equations are expressed in terms of cos theta sin. So what is happening? That is, if I consider this transformation, that is, what is the value of A1 transpose A1? That means, you know, what is that? What is A1? This is the A1. This is the A1. And if I consider this as A1 transpose A1, that means if I make the transpose, the column, it is a column, it goes into the rows position, that is this one, that is cos theta sin theta, and it is A1, that is the original one, that is cos theta sin theta. So if I multiply these two, then what is the result? Result is cos square theta plus sin square theta, which is 1. Similar thing is happening for A2 transpose A2. This is also 1. So not only this, for this total matrix A, this is also happening. That is, if I consider A transpose A, this multiplication, that means this 2, that is A transpose is written here, A transpose is written here, that is this matrix, A transpose is this matrix, and A is here, that is this matrix. So if I multiply these two, whatever the result becomes, if I just multiplication rule, there is row into column, and again the row into column by this way, first row, first column, then second row, first column. By this way, if I multiply this, and since it is a 2 by 2, so ultimately multiplication result gives us the 2 by 2, and the result is this, that is cos square plus sin square theta, which is 1. And here the term is actually one is minus cos theta sin theta, another is sin theta cos theta, which is cancelled 0. So it becomes an identity matrix. So what is actually its interpretation? That means if A is a symmetric matrix, since A is a symmetric matrix, and we get that A transpose A is an identity matrix, Thus it is orthogonal. It is earlier orthogonally transformed because off diagonal elements are 0. So look at that. Look at this thing. That is off diagonal elements are 0. So this off diagonal elements are 0. Look at this, and this. These are always 0. So in case of 2 dimensions, the number of variables is p. Where the number of variables is p, that is more than 2, we can do the same thing, and from there we can find out the each z. That means here for the actually this z is derivation of z is the main thing of the principal component. Here we can find out the value of z. For example, I can find out the value of z1, I can find out the value of z2. Similarly, if it is a p variable case, then we can find out the z, each z. So for example, if this is the matrix, that is A transpose, this looks like this, and the variable vector is this, then what is the result? That is, so like before, that is z is equal to A transpose x, and where z1 is what? Z1 is A1 transpose x. And what is the meaning of A1 transpose and x? X is this matrix. And if I multiply this is the first principal component. This is the second principal component. As per the number of variables are p there, so you obviously get the p number of principal component. So you obviously get the p number of principal component from the original matrix, original orthogonally transformed matrix X. And for example, you may say that the Z1 is the first principal component, Z2 is the second principal component, ZP is the pth principal component. But now you can calculate their variability, their variances. You can calculate, that is Z1, and now this Z1, Z2 are arranged by such way that is when I do the principal component, what is important, that this from these relations, that is Z is equal to A transpose X, if you derive Z1, then if you derive Z2, this derivation of Z1, Z2, Z3, and so on, Zp are derived by such a way, that Z1, that is the first principal component, carries the maximum variability among all J's. Among all J's mean what? Among all J's mean without himself itself. That means it varies from J, varies from, because it is the first one. So among the others, that means 2, 3, 4, 5, and so on. If there are 10, so if without 2, 3, 4, 5, and 10, Z1 has the maximum variability. Then Z2 is what? This is the second principal component, carries the next maximum variability, where the where after Z1, and where the J is varies from 3, 4, 5, and P. That means without considering Z1, Z2 is the next principal component which carries the maximum variability, and where the variable among the variables 3, 4, 5, and P. Similarly for 3, and so on we can construct. That means what? That means the rule follows here, the construction of Z is done here by such a way that variance of Z1 is maximum, variance of Z2 is second maximum, and so on. Variance of ZP is minimum. So you can range the principal components, you can rank the principal components by such a way in terms of variances by this way. That is considering this thing, that is A transpose A is equal to 1, or AJ transpose A, AJ is equal to 1 for any kinds of J, 1, 2, 3, and P. So this is an important thing. This is actually how the PCA derives. For example, I am given the earlier example. That is, for example, suppose in our some example, the Z1 is the first principal component which explains, suppose, the 66% variability of the data matrix. Z2 is the second principal component which explains, suppose, 23.22% variability of the data matrix. Z3 is explained 5.05% variability of the data matrix. Z4 is the fourth principal component, explain 1%. That means, look, first principal component explain the variables variability by the highest percentage. Second one is the next highest. By this way, the variability of the principal components are reducing. So from these things, that means from this varying variability, you can identify which principal components you have to choose them for the further discussion or your regression or your multiple regression. So such variability, we found that here, for example, in this example, we here found except Z1, Z2, Z3, all other principal components explain very insignificant variability over the data matrix. So among P, that means if you have the P number of variables, then you get the P number of principal components, but they will be arranged in terms of the variability. So such variability, that is among the P number of variables, we get P dimensions, and we can now decompose it into the by lowering the number of dimensions Z1, Z2, Z3. That is, we are considering it in terms of the 3 dimensions. So this is the main story. And if the data matrix, in terms of the data matrix, it is considered as which one are the best PCs, that is 1 minute. Which is the best PCs, that is identified by the variance, that is variance of Zj. If jth principal component is the best, then we have to calculate that variances. Now what is the value? Z is nothing but A transpose X. That means if it is Zj, that is Aj transpose X, and Aj transpose X, its variance can be written as Aj transpose variance of X, Aj. So what is variance of X? It is identified, if I consider it in terms of the population, then it is identified as the diagonal elements are the variances and the off-diagonal elements are the covariances. So it can be written as in the form of, that is variance of X. If it is sigma, then I can write it as Aj transpose sigma Aj. And you have to find out the order of this Aj transpose, because order of what? Or the order of, for example, if there are P number of variables, then what is the order of Aj transpose? That is 1 cross P. And what is the order of sigma? It is P cross P, because P number of variables are there, so it is a symmetric matrix, and its order will be P cross P, and the order of Aj is P cross 1. So by this, you get the thing as in the form of scalar, because if you multiply all the order, to find that it is a values is a scalar. That's why this 66%, this 23.22%, this variability comes. That means it will comes as in the form of a scalar. So now just for further I'm coming to some example. That is after getting the A transpose X matrix, then you find out its mean, you find out its variance. Then if you find out its distribution, then you consider, suppose it is normal distributions, then you consider its normal distributions over the variables, and you find that the thing is that the population PCA, if you consider it with a population PCA, then it is normally distributed over the mean factor mu and the sigma, and the population parameter in terms of Z8 is identified. If you consider it in terms of sample PCA, then this mean mu will be transformed to X bar, and the sigma is transformed to S. So this kind of things is happening in case of population or sample corresponding behavior. So in the ultimate formation, when you get the principal component, we get it is in the form of a linear combination of X. Look at the earlier derived, just recall about the earlier derived results. What you get here, that is the principal components is just as the linear combination of X. So I am telling you that this Z1 is not representing X1. This Z2 is not representing X2. These are reformed. This similarly, when you use the entropy, that is combined all the variables. Here also similarly, they are combined by such a pattern, and the combination process is what? Combination process is orthogonality. So the basic working behind the software is going by such a way that okay, yes, that it is considered as each principal component is considered as a linear combination. and that is Zj is expressed by this way. So look at the way how it is find out, how we find out the principal component. That is the important thing. That is, I am showing you by some geometrical and this kind of process without avoiding the actual mathematical descriptions how it is comes. That is a part of the mathematics. That is, it may not be important everywhere, but how it is comes, that is an important thing. That is first, that is for example, first principal component. If I consider the first principal component is what? First principal component is A1 transpose X, and that is A1 transpose X, and it is subjected to what? Subjected to A1 transpose A1 is equal to 1, and that comes from that is the maximum variances, so its variance will be highest. Second principal component is what? A2 transpose X, and it maximizes the second variance, that A2 transpose and X, subject to these restrictions. And also there is another restriction, that is the covariance between these two, that is A1 transpose X and A2 transpose X is 0. So by this way it is going, and we are considering. That means what is the main thing of deriving the principal component is that we are maximizing the variability. That means after making the dimensions, after creating the dimension, we are choosing the variables. We are combine the variables by such a way that it maximize the variability, and maximize the variability with respect to what? That means when you are maximizing something, there is some subjective constraint. Since it is a constraint maximization problem, and the problem is what is the constraint? The constraint is that is the A transpose T. A is equals to 1. That is, we maximize the variance of Zj, which is identified as earlier before, if it is in the form of the sample, that is A transpose A, that is maximized subject to this. So the subjective function, that is this subjective function is equal to 1, also can be written in this way. And we use the general, those who are people from economics or geography, they know the maximization, how to solve the maximization rule, and we are using the Lagrange function. And if I using this Lagrange function, that means what? That means we actually combining this function, that is the variance, this variance, and this subjective equation simultaneously. And this thing is done by the formation of the specific Lagrange. So this is the Lagrange function, and if we maximize this Lagrange for the choices of Aj, then the result is this, because it is actually A transpose A. That means actually it is a something square. So 2S A will be the result, and here lambda A transpose A, that means 2 lambda A is there, 2 lambda I is there, because it is an identity matrix. So if I take 2 common, so ultimately the main thing upon which the PCA depends, that is this factor, that is the S. S is what? The variance covariance matrix. And lambda is what? That is the Lagrange multiplier, and I is the identity matrix. This is the famous formula of matrix algebra upon which the total things depends. And here S is what? S is a square matrix. Lambda is what? Lambda is a scalar. And I is what? It is a unit matrix. The order, order is known. And since this is a first order condition, so I can mention this as S minus lambda is equal to 0. And this will generate the characteristics equation. This equation S minus lambda I will generate the characteristic equation and also generate the characteristics root. Considering the order of S and the equation S minus lambda I, this will generate the characteristics equation and characteristics roots by such a way that when I derive the characteristics equation and characteristics roots, the eigenvalues of the different considering values of the lambda, that is lambda 1 is highest in compared to lambda 2, lambda 2 is highest in compared to other lambdas. By this way, the arrangement of the lambdas are maintained, that is lambda 1 greater than equals to lambda 2 greater than equals to lambda 3, and so on. So why the variability is also comed in this way. That is, if I doing the arrangement of the lambda 1, lambda 2, and lambda 3 by such a way, then we can solve the values of the corresponding A's. That means the variabilities. So this is the theory part. Now I am going to the the thing, that is how to solve in terms of the SPSS. So just give, so look at the data set. I consider a data set on food and smoking, and it is a simple example. I choose a simple example. I first find out the results through SPSS, and then I will go to the explanation of the results. That is my total thing. So look at the data set. That is the expenditure on food and expenditure on smoking, and if I 1 minute just. Just 1 minute, just wait for 1 minute.
Punam Devnath, you can join with the group number 14. Okay.
Is the screen visible?
Yes, sir.
Yes, sir.
Okay, just 1 minute. Okay, and it is I just put that data set here, the food and smoking, and the variables are very normal. If you go to the variable view, the variables are 2 variables, and all are I think since the stage is for SPSS, the normal SPSS operation is known to all. So I'm not it is not actually SPSS is a major thing. If you go through any software like R or Jamovi or this kind of things, everywhere it is very easy to handle. So for this, I'm just going directly into the that is PC handling. Just go to the analysis and then go to the dimension reduction. So look the steps. Steps are very easy. You just go to analyze, and then go to the dimension reduction, then go to the factor. Okay, so you bring the variables food and also bring the variable smoking, and then go to the descriptives. You can initiate, that is univariate, that is you have to show the coefficients, significance, KMO Barley. This is an important, I will come to that later. And continue this, and you choose the extraction, that is the covariance matrix is originally done, and that is scree plot. It is not needed here in this example, because scree plot is important if we consider for more than at least 4 or 5 variables. So okay, so mark a tick on it, and
Sir, would you
then
repeat the steps?
yes.
Sir, would you repeat the steps? We are not able to follow.
Okay. If I go to slowly, I otherwise just wait. I just repeat again. You just analyze, okay? Then go to the dimension reduction, and then go to the factor. this window will open and you enter the variables here. Then you go to some actually decorating the variables, that is descriptives, and if you check the coefficients, its significant levels, its determinants, its Km over rate, this kind of things, and then continue. Then you go to the extraction, and it is only done here. Covariance matrix is given, that is unrotated factor solution is there. If you interested in scree plot, I'll come to the scree plot later. Okay, this is the scree plot, and then continue, and then rotation, and that we follow the varimax rotation, and you can do by equimax and or the quadrimax by this kind of rotations. So then continue, then scores, it is okay, and display the factor scores coefficients, continue, and it is done. So click on OK. So this is the output table, that is one correlation matrix, and the value of the Km over rate. I'm coming to that, what is Km over rate test results showing, and that is the food and smoking extraction results, and the variance. This for this table is quite significant. So you find that the first variable, you just follow the initial eigenvalues, that is the first variable, that means the food, it actually explains 99.36 its variability is highest, that is it explains the 99.361%. Okay, it explains the 99.361%, whereas the smoking explain only 0.639%. So you can directly reduce the smoking from your analysis. This is the way, that is how you can remove the variables. This is the basic thing. But how it is happening, this is done with the help of software like SPSS. The process of deriving the results with SPSS is the thing. Now, if we whether the averages are there or not, no. Okay, so the thing is this, that is the variance, and the scree plot is what I'll coming to that. Scree plot is this here. The scree plot is not quite meaningful one. If I consider the more than two variables, then the scree plot is quite meaningful. So what is this? The important here it is, that is the variance of the first variable, that is 99. Yes.
Sir, in presentation, it is only data variable. So that the output.
Output is not visible.
No. Output is not visible.
Okay. Just wait. Is it showing? Is it visible now?
Yes, sir.
Okay.
Yes, sir.
So look, this is the when I click on the OK, and then this output will be generated, and you know how it is done already in different kinds of SPSS operations. And here the important table is this. In case of such a small data, that is what we are dealing with. The important table is this. That is like there are two components. Then look at this thing. What are the variables? Food and smoking. But here I am not telling these are the food and smoking, because they are the combining components of some food and smoking. The first component is what? It explains its initial eigenvalues explain 99.361% of the total variability. And the component 2 explain only 0.639%. So you find that it is easy for us to consider the first component, that is going through the first component, that is the percentage of the variance is 99.361. That means we have to deal with first component and not to extend the component and consider the behavior of the variability of the first component is highest. If it may be the result may be by this way. If you consider more than one variables, then the different components will be derived, and they are arranged by their variances. So you can choose highest variability, highest variances components, and without considering the lowest one. This is the main explanation. Now, what kind of things is actually happening? Just I am go to that. One minute. Yeah, the screen is now come, na? Okay, the screen is visible. The data set. The data set in the word page, is it visible?
Yes, sir.
Yes, sir.
This is the data set which I actually run through the SPSS. Now, what the data set gives us, that is, if we extract the data set, PCA gives us the following results. That is the variance covariance matrix. That means just don't think about the PCA. Suppose this is a variable. Suppose these are the variable. This is the food expenditure and this is the smoking expenditure. And you place these two columns in Excel. Suppose. Then what you can do, you can if you are quite familiar with Excel, you can find out the variances, you can find out the covariances. Suppose Excel calculate these variances, the variances of between the food and food, that is the variances 1.55, and the variances between smoking and smoking, that is 29.56, and the corresponding covariances are 5.76. Now the results is derived, which is in the SPSS. Now consider our learning, what we learned earlier, that is, consider the matrix S minus lambda is equal to 0. What is the operation? And what is S? S is this variance covariance matrix, that is 1.15, 5.76 and 5.76 and 29.54, and I is the identity matrix, and we do not know the lambda. We have to find out the lambda. Okay, so I just doing this operation. The same thing, that is the S matrix minus lambda I. Then I add subtracting these two matrix, so it becomes lambda 0, 0 lambda, you know. And when I am subtracted, the new matrix becomes this. That is I 1.15 minus lambda and 5.76 minus 0 and 5.76 minus 0 and 29.54 minus lambda. And if I find out the determinant of this, and this is setting equals to 0, because original thing is what? Original formula for extraction of the dimension is this, that is S minus lambda I determinant is equal to 0. So if I find out this S minus lambda I for this case, only the variance, only from the knowledge of variance covariance matrix, look, what is the breaking rule of the determinant? Multiply this 1.15 minus lambda with 29.54 minus 5.76 minus this value in this diagonal values, that is 5.76 into 5.76. So this is the result. That is, this is the result is equal to 0. So if I break this result, if I make the results, that is solve the results, that if I multiply this 1.15 with 29.54 and this again that with that, then I get a quadratic form of equation. The equation looks like this. That is lambda square. This is the form lambda square minus this plus this is equals to 0. So from where we know this is a quadratic equation, so it must have two roots. Roots are what? Lambda 1 and lambda 2, and we can apply Bhattacharya, that is minus b plus minus root over b square minus 4ac by 2a. And if I apply this to formula, here for this quadratic equation I get lambda 1 as 30.66 and lambda 2 is 0.03. These two are the eigenvalues. These two are the eigenvalues which are actually shown by the other software, like SPSS is also shown this, and the other software EViews or Jamovi, these are clearly mentioned that these are the eigenvalues. So what is the calculation of the eigenvalues is this. I'm just showing you, I'm just giving you the idea by considering the two variable cases. So the eigenvalues are this identified as lambda 1 and lambda 2, and we put the lambda 1 and lambda 2, this lambda 1 and lambda 2, we put this in this equation, that is S minus lambda I aj. So first consider the value of lambda 1, because there are the two lambdas. So if I consider the values of lambda 1, that is 30.66, and if I put this in this matrix, that means this result, remind that this equation, this is the equation. S is what? That is variance covariance matrix, minus lambda is what? Lambda is lambda 1, that is 30.66, and I is what? That is 1001, and A1, because for the first this equals to 0. And what is A1? We know earlier that A1 is nothing but this A11, A12. So I just put it again, and this is the thing. And from here, I just solved this part, that is within the matrix part. That is this 1.15 minus 30.66, the value is minus 29.51, and this 5.76 remains here. And 29.54 minus 30.66, that is minus 1.12 into A1, A2. That means if I apply the matrix multiplication rule, that means what is the rule? That is this column, this row multiplied by this column, that is this A11 into 29.51 plus 5.76 into A2, this equals to 0. And this again 5.76 into A11 minus 1.12 into A2 is equal to 0. From this equation system, we do not get any unique solution because both are equals to 0. Because what? Because we do not solve the A11, A12 from these two equations, because both are equals to 0. Infinite solutions we have to get. So what we have to do? Then we apply that subjective restrictions. That is what? That is A1 transpose A1 is equal to 1. So what is A1 transpose A1? What is A1? You just get right here earlier. That is A1 is nothing but this. A1 is what? A11, A12. So look at this. If I make the A1 transpose, the column vector now transpose to row vector, and the original is the column vector. So if I multiply this A11 is multiplied with this A11. So result is what? A11 square, and A12 is multiplied with A12 square is equal to 1. That means what? That means from this relation you have to find out A12 as root over 1 minus A11 square. So now put this A12 here. Suppose you consider the first equation, that is which is derived. Now put that A12 here. So if I put this A12 here, then the first equation becomes this. Then solve the value of A1. Just transfer this 29.51 A11 into the left hand side and making it square, and find out the value of A11, and we find out the value of A11 is 0.19. And what is A12? That is 1 minus this, that is 0.98. Thus from here we can these are what? These are the factor loading. The software gives us the factor loading. These are the loading amount of the factor. So lambda is, if lambda 1 is considered as 30.66, just 1 minute. Then we have two factor loadings. And what are the factor loadings? Factor loadings are 0.19 and 0.92. Similarly, do the same calculation for lambda value, is do the same thing. Here you frame the equation for lambda is equal to 30.66. There is another value of lambda, that is 0.03. And you put here 0.03. And here you put here A2, that is A12, A22. Then you calculate the A12 and A22, the other two factor loadings, and solve that. You find A21 is 0.98 and A22 is minus 19. That is not shown here. So we can consider these two principal components are derived here. 0 point this and 0 point this. So look at this values of lambda. Now what is lambda gives us? First lambda value is what? 30.66. And second one is what? That is 0.03. So what is the total? That is 30.69. Okay. First lambda 1 is what? 30.66. Second eigenfactor is eigenvalue is what? 0.03. That means what is the total value? That is 30.66 plus 0.03. That means 30.69. So find out what is the percentage of 30.66 out of 30.69. That means it is that percentage, 99 point something, that is showing by the SPSS results. And what is the percentage share of lambda 2? That is 0.03. So that means it will identify you that here the second principal component is not important, not significant to you. You can run the multiple regression or any kind of things with the help of only one principal component. Okay, so that is actually under the model adequacy. That is, I find out lambda 1 is 30.66 and lambda 2 is 0.03. So we find out the summation of lambda, that means 30.66 plus 0.03 is, that is 30.69. So actually you have to extract it lambda j from the matrix and from the variance covariance matrix. And now look at the beauty. What is the beauty? That is, look at the trace of this matrix. Trace means what? Trace means the summation of the diagonals. That means 1.15 and 29.54, and that is 39.69. That is lambda summation of lambda. This is the process by which the principal component is working. So we can say that what is the trace? What is the sum of the diagonals? That is also the sum of the lambdas. Trace elements of the matrix means the sum of the diagonal elements of the matrix, and that is also summation of lambda, summation of all kind of lambda what we define. So if I generalize the elements, so if I generalize the case, for example, this is a variance covariance matrix, and there the traces are these diagonal elements. That means these are nothing but the variance. These are actually the variances. That is S1 square, S2 square, and SP square. And sum of the all variances is equals to sum of the lambdas. So summation of lambda gives you the you can generate the ideas of summation of lambda from all the trace values. So now if you have to express the percentage of one lambda out of this trace, then you can find out the variability, which is the maximum variability. Which principal component is max, and the principal component process is deriving by such a way that maximize the variability. For example, in our earlier considered example, if I considered A1 as we derived earlier, that is A1 is 0.19 and A11 and A12 is 0.98, and the S matrix is this, then if we defined by this way, look, that is A1 transpose S A1 is 0.19 and 0.98, then S is you know that value of S, that is variance covariance matrix, and then its then the original matrix there, that is first one is transpose, that is 0.19, 0.98 in row form, then the variance covariance matrix, then the column vector, and if you multiply the result gives you the first values of the lambda, that is 30.66. So why the result of such kind of things, that is trace is equals to summation of all lambda will come. Now you can do the statistical, you can run the multiple regression now with those components which are significantly contribute. So you can run the statistical inference and statistical inference for unbiasedness, and that is a different part that you can apply in the normal, if it follows the normal distribution. I will not come to that. I just so yes, yes, it is not important. So what are the important steps of PCA? How you can run the PCA by any software like SPSS, but what are the important steps? You have to remind what are the important steps to run the PCA. And to do this, Barley gives us some idea. That is, this idea is generated by the Barley. That is, we have to find out the correlation matrix from the data set. It is very easy to get the correlation matrix. That means you have to find out the values of you cannot require to run SPSS. You have the Excel and you just calculate the variances and the covariances of all variables. Then you can consider the correlation matrix. And then second, go to the Barley test. And what is Barley test? I'm coming to that. That is, suppose a matrix consists of a number of variables, p number of variables, and you run the PCA. And from the PCA, you arrange the you get the p number of new rotated components, and among them p number of variables. We found that m number of component dimensions are now contributing with a significant variability, where m is very less than p. So we are removing m minus p dimensions. So in case of, for example, in case of two variables, or p is equal to 2, we can remove any one dimensions. For example, where when you remove the variable, when you remove the axis by angle theta, we are removing the x2 and considering only with x1, like this. So what we assume, for example, suppose after removal, after moving, you find the original data set is this. Suppose original data set is this. Now you transfer this axis, and again by angle theta, and again this theta, so that it remains same as a circle, or same as a circular form or sphere form. The data sets are plotted by such a way that we cannot get any clear idea after the rotation that whether there is any changes in the variability of the variables. So what do you consider? Then we consider a test. What is the test? That is we are running a regression based test. What is that test? That is we test the regression, that is the correlations levels between the variables is 1 against the alternative. The correlation is not equals to 1. So considering that data set which is given earlier, I find out the correlation matrix, that is 1, and the other values are 0.0258. That is the correlation between x1 and x2, if I consider the two variables. Then Barley gives us a specific state statistics. What is the formula? You can note down this formula. Any book you can get this formula. The formula is this, that is minus of n minus 1 minus 2p plus 5 by 6 log of r, where n is the number of observations, p is the number of variables, and r is the correlation coefficients. So if we consider this, if we calculate these statistics, and these statistics will follow the chi-square distributions. So easily, if you have the data set, you find out the correlation coefficient, you know the p, you know the n, then estimate these statistics. And if you found that it is beyond the critical region, you know the acceptance or rejection kinds of things, what you are doing in hypothesis testing, that it is beyond the acceptance level, then you actually, what we are doing, we are rejecting this null. That means the correlation is not unitary, the correlation is varied. So correlation coefficient is varied. That is the Barley test given us. So what are the steps? You first find out the correlation matrix, then go to the Barley test, and then go to the PCA if there is any sphericity. That means sphericity is a very important thing. That means if the data set are plotted by such way, after rotation of axis, you cannot find out which variable is a important one or which variable is not important one. You cannot find out. Then you have to go to this kind of test like Barley gives us. So the most significant part, that a variable matrix, suppose of some order, is given to you, and you can do the PCA. Now there are the several criteria that means we have to follow. First one is what? That is what we gathered from such discussions, that we can find out the percentage of each and every lambdas. Which lambda gives us the maximum value of the percentage, that will be considered, and which is the minimum, that will be discarded. This is the basic principles. For example, in our earlier example, lambda 1 is what? 30.66. Lambda 2 is 0.03. And so total lambda is 30.69. So what is the cumulative variance? If I consider the cumulative variance percentage, again making its percentage, that is 30.66 divided by 30.69, that means the value is 0.999. And the second for the lambda 2, it is 0.001. That means it explains 99%. And the lambda 2 explains only 0.1%. So from here you have to make the idea which one is explaining the most. Second one is the average root. That is when you get the lambda, then make the average of the lambda, and if you find the average values of the lambda, and if you choose those dimensions, that means the question is when it is a z variable matrix, z in variables are there in a matrix, then you have get z component, but they are arranging in terms of their variability. Now the question is up to which level I have select. First one is given us by that way, that is the cumulative percentage, that is the one way. Then there is another thing, that is the average root, and that is done by such a way that you have to find out the average lambda and divided it by the number of the variables, and those lambdas are above the average, you have choose that is the average root rule. Kaiser rule is there, that is what is Kaiser rule, that is you have to find out the correlation matrix, then you find out the trace, and trace is obviously equals to 1 1 1 1 1 if there are p number of variables, so the sum will be p, and then you find out a statistic, that is xij minus, that means you standardize the variable and find out the standardized variance also. But the standardized, if you transform the variables into standardized forms, you know the mean is 0 and the variance is 1. So keep those lambda, that means when you get the lambdas, if we keep those lambda for which the lambda g is greater than 1. This is another rule, this is given by the Kaiser. There is a broken stick method. What is the broken stick method? That is if there are, suppose 3 variables are there, then you consider some indexing by making that is 1 by p summation 1 by k, where k varies from j to p. J is the number of the variables 1 2 3, and p is the number of variables, that is 3. So we can form the L1 and L2 and L3 by this way, that is 1/3 into 1/3 plus half, 1 by 1 plus half plus 1/3, and the second one is 1/3, first one is removed, that is half plus 1/3. L3 is formed by this way. So here L1 corresponds to first eigenvector, eigenvalues. L2 is corresponds to second eigenvalues, and by this way we can form, as per the number of the variables, we can form the different numbers of eigenvalues, and considering that depending on such values of L1 and L2 and L3. From here, what is found at that first value is 0.61, second one is 0.27, third one is 0.11. So you can arrange L1 is greater than L2, greater than L3. By this way, you can find out lambda 1 is greater than lambda 2, and you get lambda 3 greater than lambda 3. So you can construct the lambda by such a way, that is lambda j is lambda j by summation of lambda j. That is, if you consider first values, first L1, that is first L1 is 0.61 and second one is 0.28. By this way, if I consider the values of lambda 1, lambda 2 and lambda 3, then we consider by this way, that is the average, that is lambda 1 is explained 0.67 divided by this 0.67, 0.21 and 0.05, that is 0.72%, 72%. Lambda 3 explained 22%, lambda 3 explained 6%. So by this way we can construct the variability, and that is the thing. And what is Cree plot? I am coming to that last one. That is Cree plot is this. That is, I arrange the principal components in a diagram, and when I get, suppose it is a 3 principal components. Suppose there are 10 variables and it is divided in 3 principal components. So when one elbow point, that means if a point is find out, that is in the first example what I am telling to you, that if we find out any elbow point, then up to that, how many principal components are there, I have to select. For example, here I can select up to PC7. That is 7 principal component we can select from first, second, third, and so on. Beyond that, all the principal on the line, if the drawing line becomes horizontal. So this is the explanation of the thing, that is how you have to choose or this. So I'll stop here today, and there are so many kinds of things, like so many things are also there. Like that is, you can go through the book, that is test for rejecting. You may do the rejection test when one principal component is whether this principal component is accepted or rejected. That can also be done by different kinds of tests, and there is a significant role of Barley also. So this is the part I think actually I am not dealing with the space related part majorly, but what I am trying that students are doing what they are getting the data and they are knowing the steps of the spaces and then run it, but they are not able to explain what is happening the data. So I am trying my best, that is to give you it is I think some though people which are who those who are not from the background of pure statistics or mathematics, it is quite difficult, but I just give you the sense with considering the small and some very insignificant calculation type based examples, that is how the things are working. That means that is principal component is nothing but that means it gives us the new dimensions created from the extraction of a matrix which are varies in terms of the variable, and from that variability you have to choose the new dimensions, and then you run your purpose or research objectives. If it is related with multiple regression, if it is related with any type of comments, if it is related with map drawing of the geographic variables, then that can be done. So before that you have to understand the background working. That is very important. The software running or these kind of things are not very important. This can be done by a layman also, but you have